Dear students, welcome to today's class. The topic of today's discussion is various checks in slab. Normally, after design of one-way slab and two-way slab, we have to carry out few checks on the design data which we have gathered. So, to carry out all the checks, this lecture has been planned. So let's take a slab is there which is already designed. The informations given in this design slab is that the slab is provided with a steel reinforcement 10 mm diameter, that is 10 phi, at the rate of 198 mm center to center along shorter span and long span also. Total factored load on the slab comes 9.75 kN per square meter. The overall depth of the slab is 100 mm and size of the slab is 3.5 meter by 3 meter, resting on 300 mm thick walls. Take M20 concrete grade and Fe415 steel. Check it for deflection, cracking, LD, that is development length, and shear. So these are some various checks we have to carry out to check the design is okay or not. Now, with the given informations, if we take a sketch of the slab and we show the given informations, that is the main steel along shorter span is 10 5 means 10 mm diabar at the rate of 198 center to center. Again, along longer span, the same diameter of bar and same spacing 10 pi at 198 center to center given. The total depth is D 100 mm. Now, as the 10 mm diabar is given, and we generally provide 20 mm clear cover, so we will calculate from here the smaller d, that is the effective depth, 100 minus 10 by 2 minus 20, and we get 75 mm as the effective depth of the slab along shorter span. And similarly, effective of the slab along longer span is 75 minus 10, that is 65 mm. So this way we have got the effective depth in shorter span as well as longer span. Now we should know what is the effective span in this case. So the effective span in this case is 3000 clear span, that is the shorter span 3 meter. So 3000 plus small d 75, 3075, or center to center span, that is 3000 plus half the wall thickness, so this is 3300, and smaller these two is 3075 mm. As we have been given here the 10 mm diameter at 198 mm center to center, so from this data we can calculate the corresponding area of tensile steel. So that is steel area AST comes 78.5 1000 divided by spacing 198, so 396 mm square. So we have these informations. Now with these informations we will now start the checking process. Now the first check is check for cracking. So as per IS-456-2000 page number 46 and clause number 26.3.3.b, there are the guidelines for checking for cracking. So in this we generally check the spacing between main bars and even distribution bars in one-way slab, and any bar we have to check the spacing between the one bar with its neighboring bar. So first option is the spacing between bars should be 3D, that is 3 into 75, 225 mm. Maximum 300 mm is allowed, and given spacing in this problem is given 198 mm. So out of these three, the smaller value is 198 mm center to center. So we have been using given in this problem, so it is okay. Now along longer span, the spacing between bars is, since it is also a main bar, so it is 3D, 3 into 65, 195 mm, and maximum 300 mm. So given 198 again. So out of these three, the shorter is 195 mm. but where the slab has been given spacing 198 millimeter center to center, so 195 is the correct spacing, so we should provide 10 mm diameter bar at 195 center to center. So through check there has been a correction here in spacing of the longer span steel. So this way correction is checking is important. And the second type of checking which we should do is check for deflection. So this check for deflection carried out to check the deflection is within limit or not, because cracking in the tension zone takes place because of deflection. Deflection means the creation of curvature in the slab surface. So as per IS-456-2000 page 37, 38 and 39, for given slab Ly by Lx, that is 3.5 by 3, 1.66, that is less than 2, is a 2A slab. So according to 2A slab, the allowable L by D ratio is 35 into modification factor and into 0.8, that is a Fe415 steel. So here we need to calculate modification factor. So the AST given is 396 millimeter square. So the percentage comes AST by BD into 100. So putting all this, we get 396 over 1000 divided by 75 into 100 comes 0.528%. So for this percentage of AST is the actual percentage in the slab already designed. So from this data and from page 38 of code figure 4, we get modification factor equal to 1.2. So putting this factor in this equation, L by D equal to 35 into 1.2 into 0.8, 33.6% value comes the ratio of L by D, 33.6. Now this is the allowable ratio. Now what is the actual ratio in the slab? So actual L and actual D. So effective span is 3075 divided by D 75. So this comes you can see here, this is 41. 3075 by 75 is 41. Now the allowable ratio is 33.6. So we can just compare these two ratio. That actual ratio is 41, which exceeds the allowable ratio, which is not allowed. So this is more than L by D allowable is not okay. So we have to recheck the design. In such a situation, the depth of the slab should be revised and the slab needs to be redesigned, because here, because of this higher ratio of L by D, the deflection may occur in the slab. So control for deflection is important and the ratio of L by D needs to be within limit as per IS code. So this is the comment of this check, that the depth is I think lesser, so this check is getting failed. So depth of the slab needs to be revised and redesigned. For the third check is check for development length, LD. Development length is provided the end anchorages to every steel, every main steel, and anchorage of the steel bars to develop its bond strength in the RCC members. So for IS-456-2000 page 44, clause number 26.2.3.3c, there is a strict guidelines about development length, that it should be less than or equal to 1.3 M1 by V plus L0. Here M1 is the bending moment at the concerned section where we need to check the LD. V is the shear force at that section, and L0 is according to IS code. Here L0 is first equal to smaller d, that is 75 millimeter effective depth. Second is 12 times diameter. So as we have been given here 10 mm dia bars, so 12 into 10 120. So L0 becomes 120 mm. So larger of these three, these two 75 and 120 is 120 millimeters. So this L0 is 120. Now this V shear force is equal to V equal to WL by 2 as in case of a simply supported beam. So 9.75 is the given load, multiplied by 3 the shorter span, divided by 2, that is 14.625 kilonewton or 14.625 × 10⁻³ Newton. So as per as per SP16, for given conditions, as per SP16 page number 184 table 65, for Fe415 and M20 concrete grade, directly we can get the value of LD, the development length of the bar, that is 470 millimeter. So these informations we have now available. Now we will calculate what is the moment at the concerned section, that is M1 equal to 0.87 Fy AST into D under bracket 1 minus Fy AST divided by FCK BD. So this equation is given IS code. So according to this equation, this is equal to putting all the values. We have all the values. AST we know, Fy is 415, D we have 175 millimeter, FCK is 20, B 1000, D is 75. So putting all the values, we get bending moment 10. This is 9.546 into 10 to the 6 Newton millimeter. Now putting everything in the given LD equation, that is L 1.3 M1 by V plus L0, 1.3 M1 9.546 10 to the 6 divided by V plus 120. So putting all, we get the total of this equation is 968.53 millimeter, that is more than LD 470. So LD is lesser than 1.3 M by V plus L0, that is 968. So this check is okay. So the slab is safe in as per the development length of the bar is concerned. Now the fourth check is they check the slab for shear. As we know that the shear reinforcement is provided in beams as their depth is more, but the depth of the slab is smaller, so shear reinforcement as such is not provided in RCC slabs. But for a clear-cut idea that what is the status of shear force in slab, so there is a shear check according to SP16, rather it is according to IS-456-2000 page number 72, clause, this is 40.2.3.1. the nominal shear stress tau V equal to VU by BD. VU is the shear force and BD is the effective cross section area. So 14.625, this we have already calculated. VU, that is 14.625 10 to the power 3. So this divided by 1000 and divided by 75, we get 0.195 Newton per millimeter square as the nominal shear stress. Now for this we need the percentage of actual steel in the slab. So PT is AST by BD into 100. So 396 into 100 by 1000 into and 75. So we get 0.52%, 0.528% of the steel area in the slab. Now as per IS-456-2000 page number 73, table number 19, for this percentage 0.52, we can calculate the shear stress in concrete, the permissible shear stress in concrete. So for this percentage we have to calculate directly. We get between 0.75 and 0.5, that we get 0.48 and plus 0.56 minus 0.48 divided by the range 0.75 minus 0.5 and multiplied by 0.528, which is our value, minus 0.5. So with this we get tau C is 0.4889 Newton per millimeter square. That is the permissible shear strength of concrete, and the total depth of the slab is 100 millimeter as we have given in this problem. So as per IS-456-2000 page 72, clause number 40.2.1.1, we get a coefficient K for a solid slab 1.3. So we get a product of K and tau C, this K and this tau C, that is 1.3 into 0.4889, and this is tau C dash, it becomes 0.6355. Now you can see here the tau C dash is 0.6355 and the tau V that is our nominal shear stress because of given load is 0.95. Now here the tau v is lesser than tau c dash. So the stress due to shear force applied external load because of applied external load is tau v, which is less than the effective shear strength of the slab, shear strength of the concrete. So the slab is in a safer stage, so this is okay. So this way we have completed the 4 important checks for slab, that is check for shear, the slab is safe in shear, check for development length LD, so this check is also safe in this slab, and check for deflection. We got that the slab is not safe in deflection. Here the slab depth is not proper, so it is to be redesigned. And the check for cracking of the slab, that is the spacing between bars, is okay, but for longer span there is a revision in the spacing, that is the spacing has been reduced from 190 to 195. So this way we have completed the most important checks which is applied on the slab design, and this is applicable for all types of slab, either one-way slab or two-way slab or one-way continuous slab. So I think with these informations you would apply various checks whenever you design a slab. So with this, thank you very much for listening to this lecture.